In this video, I'm going to show you how to cycle through the powers of I and find a pattern that lets us compute I to any power pretty easily. So here we want to compute I to the ninth, and we're going to start off by just cycling through the powers of I to the first, I to the second, I to the third, fourth, and so on, and we're going to see a pattern here. So let's just go ahead and do this. I to the first is just I squared is just -1 by definition of the imaginary unit. Then I to the third, well, you just multiply I squared by I again, and then you get -1 times I, which is just -I. Then I to the fourth, we can think about that as I squared times I squared. Exponents add up to 4. Then that's just -1 times -1, which is just 1. Okay, so then if we continue this, since we're back to 1, I to the fifth would just be like I to the fourth times I, which would just be 1 times I, which would be I, and that'd be back where we started. So these are the key powers here. I to the first, I to the second, I to the third, I to the fourth, I -1, I 1, and then it just keeps on repeating over and over as we cycle through the powers. So let's just write that down really neatly over here. I to the first equals I squared equals -1, I to the third equals -I, and I to the fourth equals 1. And this is what we're going to use to find the power I to the ninth. To compute I to the ninth, we can just break that up. We can break 9 up into 4 plus 4 plus 1 using powers here. So that's I to the fourth times I to the fourth times I to the first. And we know what each of these powers of I are. I to the fourth is just 1. So this is just 1 times I to the first is just I. So the end result, I to the ninth, is just I. And that's it. So there is our final answer. I to the ninth is just I. Here's another example. This time we want to compute 3I to the sixth plus 2I to the eighth. And we're going to do this again using the key powers of I to the first through I to the fourth. Let's just compute I to the sixth and I to the eighth individually, and then we'll just plug in the results into this and simplify. So I to the sixth. First, let's start out with I to the sixth. So I to the sixth, that can be written in terms of these powers. 6 is just 2 plus 4. So we can make this into I to the fourth times I squared, and I to the fourth, looking at our table here, is just 1, and then I squared is just -1. So the result here is just -1. I to the eighth we can take care of in the same way. So I to the eighth, well, 8 is just 4 plus 4, so that's just I to the fourth times I to the fourth, and I to the fourth is just 1, so this is just 1 times 1, which is just 1. So now we can plug that into our original expression. So this expression is equal to 3 times I to the sixth. I to the sixth was just -1, and then plus 2 times I to the eighth, and I to the eighth was just +1, and we'll just compute that and simplify. So that's -3 plus 2, which is -1. And there we go. That is our result, -1. Here's another example. This time we've got a really big power on I. This is computing I to the 81st. So here we're going to really see the utility of using these key powers of I to quickly compute this. Okay, so I to the 81st, we're going to compute that just as usual. I to the 81st is going to be I to the fourth times I to the fourth times some amount of I to the fourths, and then eventually we're going to get down to having just a leftover of I to the 0, 1, 2, or 3. Now the big idea here is that in order to figure out how many I to the fourths we need, and also in order to figure out what the exponent on the very last I term is, all we have to do is division, 81 divided by 4. So 81 divided by 4, the whole number part is going to tell us how many I to the fourths we have. So that'll be the whole number part of 81 divided by 4. So that's going to tell us how many copies of I to the fourth we have here. And for the exponent here, the exponent is just going to be equal to the remainder of 81 divided by 4. But wait, we can simplify the situation even further because I to the fourth is just equal to 1. So this is really just 1 times however many ones, just however many is the whole number part of 81 divided by 4, and then times I to that remainder power, I to the remainder of 81 divided by 4. But it doesn't matter how many I to the fourths are in front of here. It's just 1 times 1 times 1 and so on. So this is all going to simplify to just 1, and we'll just have a result of I to the remainder of 81 divided by 4. Okay, so now let's compute what is the remainder of 81 divided by 4. Well, 80 is a multiple of 4, and 81 is just 1 more than 80, so it's got to be just 1. So the result then is just I. So I to the 81st is just I, and that's the end. We've got it. Now, to sum up what we did here is we uncovered another really cool general principle, and that is the principle that, in general, I to the nth power is equal to I to the rth power, where r is the remainder of n divided by 4. And that's going to be really, really useful when we want to compute I raised to some very large power. All we have to do is find the remainder when we divide that power by 4. That remainder will be either 0, 1, 2, or 3, and then we can just reference our table of key powers here. Alright, here's the final most challenging example. We want to compute I to the 5,434th power plus I to the 1,120th power. Now this looks pretty intimidating because these are really huge powers, but our general principle here, I to the n equals I to the r, where r is the remainder of n divided by 4, is going to help us out big time. So let's tackle this one first. I to the 5,434th. Let's find out what is that equal to. So I to the 5,434th, according to our general principle, it's just going to be equal to I to the remainder of 5,434 divided by 4. Okay, so now we just have to find that remainder, and we can do this through just some simple long division. Let's set that up over here. 4 goes into 5,434, and we'll just go ahead and proceed. So 4 goes into 5 once. 4 times 1 is 4. Then 5 minus 4 is 1. Bring down the 4 to get 14. 4 goes into 14 3 times. 4 times 3 is 12. Subtract, and you get 2. Then bring down the 3. 4 goes into 23 5 times, and 5 times 4 is 20. So subtract, and you get just 3. Bring down the 4. 34. 4 goes into 34 8 times. 4 times 8 is 32, and subtract, and you've got 2, and 2 is the remainder here, remainder 2. So this is just equal to I squared, which we know from our table that's just -1. Okay, so that's what we'll put in for this value here. So let's just circle it for now, and let's move on to the next one. The next one, I to the 1,120, is going to follow a very similar procedure. I to the 1,120 is just equal to I to the remainder of 1,120 divided by 4. And to figure out what that is, we can go ahead and do long division again. So 4 goes into 1,120 how many times? Well, 4 goes into 1 0 times, so 4 goes into 11 twice. So put a 2, 4 times 2 is 8. Then 11 minus 8 is 3. Bring down the 2 for 32. Then 4 goes into 32 8 times. 4 times 8 is exactly 32. So 32 cancels with that 32, give us 0. Bring down the 0. 4 goes into 0, 0 times. 0 times 4 is just 0. So 0 is our remainder here. The remainder 0. So then this is just I to the 0, and anything to the 0 power is just 1. Okay, so that's what I to the 1,120 is, and now we can just plug them right back into this expression here. So this expression is really just equal to -1. That's the value of I to the 5,434, and then plus 1. That's the value for I to the 1,120, and you add those two, and it just simplifies to 0, and that's it. So that's our final result. Final result is 0. So now we know how to evaluate the powers of I. Even for very, very large powers, we can just use this general principle and our table of key values. And this idea will be very useful in the future as we learn more and more about complex numbers and have to do more complicated operations with them.